guys, I'm Jade. Lovely to meet you. So the Schrödinger equation is one of those things that pops up a lot in like quantum science articles and journals and stuff, but the journalist doesn't usually go into what it means, which is fair because it's a fairly complex topic. So today I just wanted to share with you guys like what it actually means, so next time you read it in an article, you can get a better gist of what it's about. So the short version is, the Schrödinger equation tells us everything we can possibly know about a quantum system. It's basically the F equal ma of the quantum world. If you throw a ball and solve F equal ma, you can predict its position and momentum for any moment in time. Once you have these two, you can derive basically everything else you could possibly know about it. Velocity, energy, etc. But when we get down to particle land, Newton's equations don't work anymore. If we put a particle in a box and we want to know where it is, F equal ma just doesn't cut it. The Heisenberg uncertainty principle says that we can't know both the exact position and momentum of quantum objects, but we can know other things, like the energy levels and the wave function, which we'll explore in this video. But that information is all inside the Schrödinger equation, and with some hardcore mathematics, we can tease it out. Now, the long version. So before I get started, I should say that this is the time-independent version, meaning that it doesn't involve time. And if at any point throughout the video you get lost, don't worry. Even Schrödinger didn't know exactly what his equation meant. So let's say we have a quantum system, an electron in a box. We want to know everything we can about this electron so we can make predictions. Where it might be, what energy level it might be at. These answers are all buried within the Schrödinger equation. So first, let's start with this guy, the pitchfork thing. This is the Greek letter psi, and it stands for what's called the wave function. It tells you where the electron is likely to be, but not where it will be. See, quantum objects are sneaky in that you can't predict exactly where they'll be until you measure them. You can only predict where they'll probably be. Say there's this kid you know. You've grown up with them your whole life. They're locked in their room with their homework, a PlayStation, and a bed. If you had to guess where they were, you'd say there's about an 80% probability they're on the PlayStation, a 19% probability they're in bed, and a 1% probability they're doing their homework. When you open the door, you'll know for sure. But you were able to make these predictions because you know this guy. What if you had to guess where this electron is? You don't know this electron. Well, that's what the wave function tells us. It gives us the probabilities of where it's likely to be. But a big difference is that while the guy is only in one place at a time, the electron is in a superposition of all possible places at the same time. You may have heard the famous thought experiment Schrödinger's cat, who's in a superposition of being dead and alive until the box is opened and it's forced to choose a state. It's the same deal here. The act of not knowing where the electron is allows its probability distribution to be spread out over a large space, kind of like a wave. Different kinds of waves can represent different probabilities of where it's likely to be, hence the name wave function. It's a function that describes the wave shape of probability distribution of the electron. Oh yeah, and when you open the door and measure where it is, this wave probability cloud function collapses and the electron becomes a particle again. No wonder Schrödinger was confused. So that's what the pitchfork means. The wave function tells us where our electron is likely to be. Now let's take a look at this E. It represents the energies the electron is allowed to have. Now before I go into what that means, I just want to point out that the way this equation is arranged, these values are the ones we're trying to solve for. So it's telling us that, hey, if you do all this stuff, you can find out the energy levels of the wave functions of the electron. And if we know these two things, we can derive everything else we can possibly know about the particle, just like the position and momentum of a ball. But let's backtrack a sec. What do I mean when I say energy levels the electron is allowed to have? Like it's a grown electron, it can have whatever energy levels it wants, right? Well, no. In the regular world we see around us, energy can go up and down in a smooth, continuous way. But this isn't the case in the quantum world, and the reason comes from the wave-like nature of the probability distributions. Because our particle is inside the box, it has a 0 probability of being found in or outside the wall. So this means the wave function always needs to be 0 there. Otherwise, there's some probability that the electron could be outside the box, which we know it's not. That means that the electron can only have certain frequencies associated with it. This frequency is allowed as the wave function is 0 at both edges, and this frequency is not. This frequency is allowed and this one is not. So Einstein discovered that energy is actually proportional to frequency by this relation. E equals hf, where E is the energy, F is the frequency, and this h here is Planck's constant. Don't worry too much about that h for now. All you need to know is that it's a constant, which means its value doesn't change. So if only certain frequencies are allowed inside the box, and this is a constant, then it follows that only certain energy levels are allowed inside the box too. This property of discrete or quantized values is where quantum mechanics gets its name. Things that can take on continuous values in the regular world, like energy levels, can only take on certain quantized values at the quantum scale. Now let's look at the other side of the equation. We know what we're solving for, the energy levels and the wave functions. But how is all of this going to help us get there? Well, overall energy is made up of kinetic energy and potential energy. If a skateboarder is on a skate ramp, they'll be traveling at some speed and have some kinetic energy. But when they stop at the top, they still have energy. It's just transformed into a different kind. Potential energy. The entire energy of the system is just the kinetic energy plus the potential energy. And while it can move back and forth between those two states, its total value is always conserved. Sometimes, potential energy is written as a V. So this term is the potential energy of the wave function. So if this is the potential energy, that must mean that this term here is the kinetic energy. I know it doesn't really look like any kind of kinetic energy equation we've seen before, right? So here's the derivation if you don't believe me. So if we can solve for the potential and kinetic energy of our quantum system, this will tell us the energy levels allowed. And that's everything there is to know about our little electron. So what would some typical Schrödinger solutions look like? Well, to this particular problem, all the solutions to the wave functions take these two forms. And the energy equation that popped out was this. Great, Jade, so what the hell does that mean? Well, the first thing to note is that every term in this expression is either a constant or a whole number. H bar is a constant, 2 is obviously a constant, m, the mass of the electron, is a constant, pi is a constant, and L, the length of the box, is a constant, and N stands for the different states of the electron, and they're all whole numbers, 1, 2, 3, etc. So then the energy E can only have certain values. It's quantized. But what about the wave function? Where is the electron? Well, let's look at this guy when the electron is in its first energy state, when N is equal to 1. We get this. That's one of the wave functions of the electron, and if we square it, we get the probability distribution, aka where the electron is likely to be. We can see that there's a high probability that it'll be found in the middle here, but a 0 probability it'll be found right at the edges. Here are some more wave functions and probability densities for other energy states. See how the wave function is always 0 right at the edges. This took me an entire semester of a physics degree to understand, and what really helped me was working through a lot of problems and taking the time to build a strong intuition. So guys, please be honest, do you understand the Schrödinger equation a bit better now? I hope you do, but if you don't, please feel free to give me any feedback on how I can make my explanations better for future videos. Quantum physics is so cool and I really don't want anybody to miss out. So yeah, that's all from me. Bye!